Take a look at the title of this lesson, Polynomial Functions that have imaginary roots. Now, you guys did imaginary roots in Algebra 2. But notice under that it says Descartes' rule of signs. That's probably something you haven't ever messed with. You feel like you've heard it? Okay. René Descartes is who that's named for. And René Descartes was just a brilliant mathematician, and much of the mathematics that you learn is credited to him. In fact, the XY axes, it's called the Cartesian coordinate system. He's the one who developed that. No, the one that we do, the XY, it's the name of it, the formal name of it's the Cartesian coordinate system, named for René Descartes. Okay, the degree of a polynomial identifies the number of roots it will have. You know that. If you have a quintic polynomial, how many answers are you going to have? 5. However, not all of the roots have to be real. It's possible that some of the roots will be imaginary. You remember solving quadratic equations back in Algebra 2, and you'd get I as part of an answer. All right? That means those curves never cross the x-axis. Okay? I do need you to know that imaginary numbers are used in electricity and they're used in engineering. I don't know where else, but I know in those two places they're used. Don't ask me how they're used, I don't know. Okay, we've got 2 functions here that we're gonna specifically discuss. Look at these functions f and g. Look at that first question. If the graph is shifted up or down, we're going to leave the x and y axes where they are. If we shifted this graph up or down, what's the maximum number of zeros this graph could have? 30, right. What about g? 4. If we shifted the graph down where the x-axis was right here, that graph would cross the x-axis 4 times. That's one of the reasons that you know that that's a degree 4 or quartic polynomial. Right here. Based on the maximum number of zeros that the graph could have, what type of function is graphed? What's f? F is a cubic, and g is a not quadratic, quartic. You'll never miss that again. Ever, ever. Based on the graph, identify the number of positive, negative, 0, and imaginary roots of the function. I want you to look at f. How many of its roots are positive x values? None. How many of its roots are negative x values? 1. How many of its roots are actually x equals 0? None. But we've got to have 3 because the thing's cubic. Where are the other 2? They're imaginary. Mm-hmm. That's x equal negative 4. Yeah. What about g? How many positive zeros are there? 1. How many negative?
1.
How many times is 0 a root? None. So how many imaginary roots do you have? 2. And you know this because the sum of the zeros have to add up to give you the degree.
So there's no actual visual on the graph?
Say that again, Brooklyn.
There's nothing visual. So you got to use some. What is it?
I know because of the sum. Yeah. Yes, sir. Oh, snap, I forgot. State the left and right end behavior of the function. Look at f. Go ahead.
Like what would it look like if f(x) there's 0, 0, because
State the left and right end behavior of the function. Now, it also could look like this, but it would cross at the origin. That's when x is 0. Left and right end behavior. As x approaches negative infinity, f of x approaches, and as x approaches infinity, f of x approaches. On f, as x approaches negative infinity, the function approaches negative infinity. As x approaches infinity, the function approaches infinity. Yeah. And let's talk about g. As x approaches negative infinity, and as x approaches positive infinity. What is the function approach on g as x approaches negative infinity? Negative infinity. What about as x approaches infinity? Negative infinity as well, right? Okay, let's look at these 3 bottom questions. You notice all this page is doing is just pulling everything together. Based on the degree and the end behavior, what is the leading coefficient, positive or negative? Look at F. Is the leading coefficient positive or negative on F? Positive. What about G? Good. Based on the graph, what factors are guaranteed to be factors of the equations of F and G? Look at F. X equals negative 4, so x plus 4. Good. Are there any others on that one? Nope, that was it. What about on G? X plus 3 and x minus 3. Good. Let's talk about range. Please know that the domain of a polynomial is all real numbers. Talk about the range. What's the range of F? All reals. Or you can write negative infinity to infinity. What's the range of G? How do I write it? Negative infinity to 5. Is 5 included? Does y equal 5 have an x value? You betcha. I'm trying to keep up. Okay, the notes will be posted.
Okay.
On a polynomial, the domain is always all real numbers. Yeah. Roots of a polynomial function are going to be positive, they're going to be negative, they're going to be 0, or they're going to be imaginary.
Blood.
The fundamental theorem of algebra says if a polynomial function of degree n will have exactly n roots. Hopefully that makes sense to you. Remember, roots and zeros and solutions and answers and x-intercepts all mean the same thing. That's it. Now here's where Descartes comes in. Descartes figured out a way to determine how many of those roots are going to be positive and how many of them are going to be negative. I don't know how he ever figured this out, but he did. And the thing is that not only do these mathematicians have to figure out something, it has to be proven. They have to be able to prove it. And in calculus, the 2 guys who discovered calculus, it wasn't until over 100 years after they did it that some of their stuff actually got proven. For 100 years, the mathematicians thought, oh, that's just a bunch of hooey, and they didn't believe it until finally 100 years later, it was proven to be true. René Descartes was a mathematician of his time to whom much of modern mathematics is accredited. One such concept that carries his name is Descartes' rule of signs. Okay. The maximum number of positive real roots a polynomial can have. Please write kind of small because you're going to have to write something else too. Is the number of sign changes in f of x. The maximum number of positive real roots a polynomial can have is the number of sign changes in f of x. Now the other thing you're going to write, the maximum number of negative real roots a polynomial function can have is the number of sign changes in f of the opposite of x. So those are the two things you need to put in that box. Now let's talk about what in the world all that means. Consider the function given by the equation p of x, and we're going to work with this equation quite a bit. I want you to copy this equation into this box right here. Now what we're going to do right here is we're going to find the equation of p of the opposite of x. So we're going to do what Brooklyn said, everywhere we see an x, we're going to substitute an opposite of x and then clean it up. Well, let's clean that up. Have you got it cleaned up? What's this going to give you? 2x to the fourth minus x cubed minus 8x squared minus 2x plus 3. Write that equation in that p of opposite of x box. Now, we're going to look at p of x, and we're going to decide, as I go from one term to the next, does the sign change or does the sign stay the same? What's the sign of that first term, positive or negative? What's the sign of the second term? Does the sign change? Nope. Does the sign change from here to here?
Yes.
Yep. Does the sign change from here to here?
Yes.
Negative to positive? Yep. Here to here? Nope. Two sign changes. Go to p of negative x. Sign change? Yes. No. No. Yes. Look at the words that are capitalized. The number of sign changes in p of x, which is 2, determines the maximum number of positive real roots that that function could have. At most, that function p of x could have 2 positive real roots. No more. It will not have 3. It will not have 4. It will have 2 at the most. The number of sign changes in p of opposite of x determines the maximum number of negative real roots that a function could have. This thing could have at most 2 negative real roots. It will not have 4. It will not have 3. No more than 2. Now this is the one piece of this that will make you a little crazy. The function can have this maximum number of positive or negative roots or any multiple of 2 less than that. Or any multiple of 2 less than that. These roots come in pairs. If you think about like quadratic formula, you know how it's plus or minus. So these roots come in pairs. For example, I'm right there. If a function can have a maximum of 4 positive roots, then it might also have 2 positive roots and it might have none. But there's no way it's going to have 1 or 3. If a function can have a maximum of 3 positive roots, then it could also have 1 positive root. There's no way it'll have 2. If a function can have a maximum of 2 positive roots, then it could also have no positive roots. The proof of this, we can look it up, but we will not do it in class. For this function, how many positive roots are possible? Well, we figured that the maximum number of positive roots possible were 2. But based on what we read right there, it might also have 0. It might not have any positive roots. For this function, how many negative roots are possible? Well, the maximum number is 2, but it might also have none. Multiples of 2 less than whatever the maximum is. If my maximum was 3, then it might just have 1. If my maximum was 5, it might have 5, but it might have 3, and it might have 1. So you start at that maximum and you just go 2 less. Exactly. All right. How many of the roots can be 0? Well, look at this, and I want you don't need my help to do this. I want you to factor each one of those completely. Go. Now I want you to take a look. Let's compare the factoring to the graph. If we look at this factored form, try not to look at the graph. What does this say the zeros are? 0, -2, and 1. And the multiplicity of each of those is? Is that what you see in the graph? Yes. What about here? What are our zeros? 0 and 3, but I'm supposed to have 3 roots. 0 has a multiplicity of 2. Is that visible on the graph? 0 has a multiplicity of 2, 3 has a multiplicity of 1. Here, what are our roots? 2, -2, and -1. This was a cubic. That accounts for all of our roots, correct? All have a multiplicity of 1. We good there? Now let's look at the bottom there. Based on the factors, how many times is x equals 0 a root? How is it visible in the graph? How many times is x equals 0 a root right here? Once? How can you tell by looking at the graph? Good. Doesn't change concavity, and the graph is also not tangent. The graph crosses the x-axis smoothly at x equals 0. What about g of x? How many times is x equals 0 a root? Twice? And how is that obvious on the graph? The graph is tangent to the x-axis at x equals 0. Yep. This will all be posted on the filled-in notes, so if you get behind, don't sweat. What about on the third one? How many times is x equals 0 a root? None. How is that visible in the graph? Your curve never crosses the origin. Now wait a minute. I want you to look at the factored form, and I want you to look at the answers we put down here, once, twice, and none. Could you have looked here and come up with these answers here? How? Multiplicity of x? Why just x? Because if x is a factor, then x equals 0 is a root or a 0. What's the exponent on that x right there? What's the exponent on that x right there? And we don't have. Those first two had a GCF of x to some power, didn't they? That's how you know if x equals 0 is a root. If you have a GCF of x to a power. So let's look down here. Let's look at that. We've already talked through this. Based on what you've seen, how will you determine the number of times that x equals 0 is a root just by looking at the equation? If x to the n is a GCF, x equals 0 will be a root how many times? N times. Good. Look at that last question. Is it possible that any of the roots of that polynomial are 0? No, why not? Because there's not a GCF of x to a power. Right. Now let's start talking about imaginary. You know, this is going to work out okay. Let me stop the recording for a minute. Imaginary. Let's think back for a moment to Algebra 2 and quadratic functions. Look at the quadratic function x squared plus 2x plus 2, and the graph is over there. Notice that the graph does not show any zeros, but because the function's quadratic, there have to be 2. Where are they if that graph doesn't cross the x-axis? They're imaginary. Prove it. Let's solve that by completing this, or not by completing the square. I want to do it by quadratic formula. Let's solve that equation by quadratic formula. You remember the tune? Well done. Well done. What's A?
0 or 1.
1. What's B? 2. What's C? 2. X equals negative b plus or minus square root of b squared minus 4ac all over 2a. Let's clean it up. What goes under the square root? Negative 4. Houston, we have a problem. Why?
Because you can't have a negative square root.
Okay. Ladies and gentlemen, in Algebra 2, you learned if what you're taking the square root of is negative, then that immediately tells you you're going to have imaginary roots. You remember that's called the discriminant? If the discriminant, which is the b squared minus 4ac part, is negative, then you're going to have imaginary answers. Let's go ahead and finish it. We'll finish it on number 2. What are your answers to this thing? Negative 2 plus or minus 2i. Simplify. Factor of 2 out of the numerator. It'll factor out with that 2 in the denominator. There you go. Do I need to show you where that came from? Okay. 2 times negative 1 plus or minus I over 2. Since imaginary roots come from taking square roots of negatives and using the quadratic formula, what can be said about the possible number of imaginary roots of a polynomial function? And all I will say to you is this. Do you notice you got this plus or minus here? Imaginary roots come in pairs. Imaginary roots come in pairs. If 1 plus I is a root, 1 minus I is a root. Okay? Imaginary roots come in pairs. I know you're getting sleepy. What are the possible number of imaginary roots? Now, what's the maximum number of roots this is going to have? Well, no, back up. How many roots is this thing going to have?
4.
It's going to have 4. But if it's going to have 4 roots, right? Maybe they're all imaginary. But if they're not, how many imaginary roots could I have if they're not all imaginary? Right. Because imaginary roots come in pairs, there's no way I can have 3. I'd have either 2 or I'd have none. Now we're going to finish this page and then we're going to stop, okay? Because that's where the other class stopped, I think. Can I see your next page? Yeah, that's where we stopped. Okay, so we're going to stop at the same place they did. Now you've gathered all the information needed in order to determine the possible combinations of different types of roots. Draw a table below that summarizes the possibilities of the types of roots for h of x. Okay, that's a whole lot of hoo-ha to say. Let me just show you what we're talking about. Do y'all need to, y'all are getting so sleepy. I'm so sorry. Yeah, she's not the only one. I'm saying. Now, we are still working on this same function that we've been working on a lot. Go back to the first page, I think, of your notes. What were the possible numbers of positive roots we could have? 2, that was the maximum, or we might have none. The negative, 2, but we might have none. How many times was 0 a root of this function? None. And how many times could imaginary? Yeah, I could have 4 or 2 or none. Now, I'm going to show you what this table, what I'm talking about with the table. Positive, negative, 0, and imaginary. I don't want that one. Make yourself something like that. You're going to have 4 lines in this particular, 4 rows in this particular table. That's just as crooked as it can be, isn't it? Oh, well. All right. If I have 2 positive roots, I might have 2 negative roots. If I had 2 positive roots, I might have no negative roots. With me? If I don't have any positive roots, I might have 2 negative roots. And if I don't have any positive roots, I might have no negative roots either. Those are the only combinations I can make with the numbers 2, 0 for positives and 2, 0 for negatives. How many times is 0 a root? None. 0's never a root. But what does each row have to add up to give you? Why 4? Because that's the degree of the polynomial, right? This row, the first row, if this is the case, would one of y'all, Mason, would you answer that? If we have 2 positive real roots and 2 negative real roots and no 0 roots, how many imaginary roots do we have?
0.
Wouldn't have any. What about this next row?
2. 2. 4.
Okay. Now what you're expected to do is get out your graphing calculator, and because I forgot to tell you to get it, probably only a few of you have it handy. So if you have it handy, I'm going to graph that. And I know Tristan's got his handy. If you have that thing handy, graph that real quick, and we're going to see which one of these actually is true. But as Kendra said, either way, even if it was tangent, the graph was tangent, that'd still be 2 positive real roots. So which of those rows is true?
First one.
It's the first one. That's the row that works. That's the row that's right for that particular graph. Okay. Huh? All right. If you look at the rest of your notes, all the rest of it is some practice. We will do that practice the next time I see you. Let me go ahead and give the homework to you. But you don't have to worry about doing any of it yet, unless you just want to.